In this lecture, I am going to discuss the basic uh, design principles and the things required to understand before the discussion of the consensus algorithms in the permission model. So, in distributed system literature, we have certain algorithms. Most popularly, we have BFT, that is Byzantine fault tolerance algorithm, and PBFT, the improved version of that one. But before that, I would like to discuss in this lecture to discuss few things related to smart contract, its application, the design limitations, and then a state model, a state machine you have already understand the finite state machine. So, and the relation of the use of that model in this permission blockchain. So let's start. As we know that in permission model, the users know each other. However, users may not trust each other. And that's why security and consensus are still required in the permission model. So we can run the blockchain among known and identified participants. And particularly the business applications, private blockchain can use this permission model among the closest set of participants. For example, a kind of a tracking of assets. So the permission model is very useful in the business applications and in the closed set of users. All those models are using a kind of smart contract, which is we can understand like one thing. I'm just taking the. So we can. What is smart contract? Basically, it is a self-executing contract in which the kind of, in the terms of agreement, whatever the agreement the participant, the parties are having, that agreement will be executed directly by the lines of the code they have, the agreements they have. So we can extend the Bitcoin script. You know that Bitcoin uses the script codes. So that script can be extended to ensure the execution of that smart contract. So execute a transaction only when certain condition is satisfied. So this can be ensured by the smart contract. In the figure, we have shown a very limited number of entities. It may be many more as well. So this is the source of this figure. Now, I will discuss the design limitation of these smart contracts. The first point, that is sequential execution. The transactions executed on the platform, it is in sequential fashion and which is based on the consensus. So request to the applications, that is a smart contract, whatever the request system received by the application, that is the smart contract, are ordered by the consensus. So that's why the transactions will be executed in the same order the consensus will decide. And this gives a bound on the effective throughput. That is, the throughput is inversely proportional to that. As we know that in POW, that is in permissionless model, the transactions are received by the miner, and after the successful mining of the challenge provided by the network, the transactions are added in the blockchain. Here, the request will be received, and according to the order of the consensus, it will be executed in the order that consensus will decide. And because of that, the throughput is affected, and a possible attack on the smart contract platform is also possible, and which introduce contract which will take long time to execute. The second one, a non-deterministic approach, non-deterministic execution. If you consider this Go line code here, so this is the simple loop. If we are assigning the value to n, and suppose we are having this loop, so this key and value pair will get a different value at each iteration. So iteration over a map may produce a different order into execution. So a kind of undeterministic behavior is possible. So a smart contract execution should always need to be deterministic. Otherwise, the system may lead to inconsistent states. And a solution for that, we have a domain-specific language for the smart contract. Now, execution on all the nodes. Generally, what happens, we can execute the smart contract at all nodes and propagate the state to all other nodes in the system and try to reach consensus. And consensus will, after consensus, the same state will be propagated to all nodes and verify that the states match. Now, for making the consensus, we need sufficient number of trusted nodes, because in the permission model also, all the nodes are not trusted. So there may be that the user know each other, but the possibility are there that there may be so many malicious nodes, and they may form group and they can behave maliciously. So for consensus, we need sufficient number of trusted nodes. We need sufficient number of trusted nodes to validate the execution of smart contract. So whether we need to execute a contract at each node or not, suppose this is the question. So it is not necessarily that we execute the contract at each node. We just need state synchronization across all the network. That's all. So suppose, take this example that this node have some smart contract. Execute the code on this node and broadcast its state to all the neighboring nodes. And suppose at the broadcast level, it is received to the neighboring node. They will again broadcast, and it is received to all the nodes in the network. Now, in case if the node that executes the contract is faulty, suppose this node which executed the code and broadcasted the state, and it will be the state of all the nodes. Suppose this node is faulty. Then in that situation, we can use the state machine replication model. And for that, execute the contract at a subset of nodes and ensure that the same state is propagated to all the nodes. Here, I would like to remind you the state machine is just like, you know that there are several states, there are certain inputs, and corresponding to that inputs, you may have certain outputs as well. And with the pair of the current state and some input, the next state transition table you have. So that is the state machine we are using here. So execute the contract at the subset of nodes and ensure that the same state is propagated to all the nodes. So instead of executing the code at single node, we should execute it at the certain subset of nodes. Now, a distributed state machine replication model, the steps I'm going to discuss here. So this state machine is, the idea is that the state machine, the model, we may have the copies at each node. So place copies of the state machine on multiple independent servers. Whatever the request the network receives, it will be treated as an input. Then we know state, input, transition, and the output. So the client request will be considered as input in this state machine replication model. And place this state machine model at all the independent servers. Receive client request as an input to the state machine and propagate the inputs to all the servers. Suppose this input is received by this server, then it will propagate to all the servers. So that in the previous slide, we saw that two requests has been received at different server, and now it is replicated, and the same request is available at this server also, at this server also, and at this server also. So it will be broadcasted. Order the inputs based on some ordering algorithm. Some ordering algorithm will be used here. So to order all the requests received by all the servers and execute the inputs based on that order decided individually at each server. So each server in the same order which is decided by that ordering algorithm, on the same order, each server individually will execute. And next step, synchronize the state machine across the server to avoid any failure. After execution, it will be again synchronized so that all the server will be in the same state. And the output produced by this execution will be informed to the request provided, request done by the client. Now, the permission model we have, and I talked about the state machine replication model as well. So this state machine replication model can be used here. It is a natural reason to use this state machine replication based on consensus over the permission blockchain. And the reason behind that is here the network is closed, the nodes know each other, so state replication is possible among the known nodes. Second, it will avoid the overhead of mining. We know that a lots of the power and time is consumed by the Bitcoin network, the permissionless model. So it will a drastic reduction in the requirement of the power will be. However, consensus is still required here. So machine can be faulty or behave maliciously. That's why consensus is still required. Now, if we talk about why this distributed consensus is required, if only a single node is in the system, then no consensus is required. But when there are two nodes, and suppose if kind of there are fault of like a network or partition fault, then consensus cannot be reached. So there are three types of faults can occur in distributed consensus. The first one is the crash fault. The system may be crashed. Network may be partitioned, some nodes in the one group and another node in the another group, and the no connection between all those separate group of nodes. So that is the situation of a network or partition fault. In that situation, the consensus become difficult. And the third one, Byzantine fault, that is some nodes may behave maliciously, a kind of some hardware faults or software error. It is considered as a Byzantine fault. And for that, we use certain algorithms for that. So all these algorithms we consider as a three-state. That is, suppose if there are n processes, then we will say that it is an undecided state, communication state, or decided state. So each process will propose some value, and that we say a kind of VI value, and they will exchange value among all the nodes. And after the decision on a certain value, that we say DI, that is a decision state. So suppose there are three processes, then all the nodes can propose some value, may decide, may convince on some value, that is the decision value, that is in the decided state. And if more than three processes are, and suppose this P3 is crashed, then consensus is possible. So these three states, kind of states is, and we will discuss in the next lectures in more detail about when we'll talk about the certain algorithms for the consensus. As you know, I discussed these points. So again, I'm repeating here that any consensus algorithm requires the termination that eventually each correct process sets its decision value. Like here, some decision value, each process should set its decision value at last, that is a termination. Second one, agreement. The decision value of all the correct processes is the same, that is the second one requirement. And the third one, the integrity requirement, that if the correct processes all propose the same value, then any correct process in the decided state has chosen that value. So these three requirements should be ensured by any consensus algorithms. So there are two approaches we have, message passing systems. There are two approaches, that is the asynchronous and synchronous. Asynchronous means message can be delayed for arbitrary period of time. So it is very difficult, nearly impossible to find any consensus. So a kind of randomized algorithm may exist. And in the synchronous message passing system, the message must be received within a predefined time interval. So it gives a strong guarantee on the message transmission delay. So various consensus algorithms we have, and we will explore all these algorithms in coming lecture. So if the crash or network faults are in the system, then these two algorithm Paxos and ROF can deal with. And if Byzantine fault we have, then these two algorithms, both algorithms are not capable enough to deal with. So for that, this Byzantine fault tolerance algorithm is capable enough. And this BFT algorithm also handle the crash and network failures. And that's why this BFT and PBFT are most popular one. So in the next lecture, I will discuss the Paxos algorithm, and then in coming lecture, I will cover all these algorithms. So enough for today. Thank you.